All right, so this is picking up off of the work that we were doing earlier in the week, converting between exponential and logarithmic forms. And again, we're just really using that same pattern. This is a pattern that you should have seen in lots of examples. You've practiced it a decent number of times now. And you should also have it in your notes. And so if you didn't remember off the top of your head, which would actually be expected at this point since we're still kind of getting used to it all, you'd go back in your notes and you'd find this statement. And everything we do is going to be going back to that same statement here. So notice for this first one, I'm writing the exponential as a logarithm. And so if I'm going to write a logarithm, the first thing I have to write is log. The next thing is the base, b. The base is whatever's raised to a power. In this case, that's the 7. And so this is going to be log base 7. Remember when you write that, our base is written smaller and lower. It is a subscript. All right, the next thing is what's called y up in our example. That's the part of my exponential that it's set equal to. And so in this case, you can see that's going to be the 2. So this is log base 7 of 2, then the equal sign, and then remember log always equals the exponent. And my exponent here was called x. And so that is our logarithmic form. And again, just kind of remembering why we're doing this. Once we have this whole process down, we'll then learn how we can calculate something like that, and then we'll be able to use that to actually figure out what x would equal in this sort of an equation. All right, next step, we're changing our logarithm down here into exponential form. The very first thing I put in exponential form is my base, which of course is the base of the logarithm, which in this case is 4. So we're going to do 4 to the power of, and so remember log equals the exponent. So I just go and see what was my logarithm set equal to. It was set equal to 100, and so this is going to be 4 to the power of 100. Or in other words, that is a really, really, really big number. Equals, well, it's got to equal x by process of elimination because we haven't used the x yet. But you could also see that because my exponential is going to be equal to what's called y here. You can see the y is the big number in the logarithm. And so in this case, that was being played by x. All right, so when going and making this graph, one of the things that's a little bit weird in this particular case is that I have this minus 5 on the left-hand side here. That's not typical, right? That's not what we can normally write it as. So while it is possible to deal with it from that perspective, most of you probably wouldn't want to. Most of you are going to want to change this up somehow. One of the big concepts of math in general, if you haven't yet figured this out, here's a big hint, because most people don't say it explicitly, but I try to point this out. One of the big ideas in math that will help you be successful is that if you ever see something looking like something you don't know, make it into something that looks like what you do know. And so if you're looking at this equation and saying, I can't graph it because it's not just y equals, then make it y equals. And we do that by moving the minus 5 to the other side. That means that we're going to have to add 5 to both sides of our equation. Now when we do that, that will give us the y equals that we're going for. Then we have our square root of x plus question now for you. Can I add the 5 to the 2 here? The answer there is no. We cannot add the 5 to the 2 because the 2 is trapped inside of a square root. The 5 is not. So the 5 is basically just going to have to hang on the end there after the square root. So the plus 2 is still on the inside, and the plus 5 is going to happen to be hanging out on the very end there. So now this equation looks the way that we are more used to seeing these. This is in the format that we should be able to graph it from. Now I say should because it's possible that you're still a little bit rusty on this. And if that's the case, you're getting a little bit of a reminder, a little refresher here. So when we go and graph this, every time you add or subtract, it is going to be a shift. It moves your graph up, down, left, or right every single time you add or subtract something. And in this case, we have two things that are being added. We got the 2 and the 5 added. Now, whatever you add or subtract to the x is going to be shifting it in the x direction. So that's the horizontal direction, same direction as the x-axis, right? Now, this is the one that's kind of the tricky rule to remember. Plus moves it to the left. Minus would move it to the right. And that is not just true with square root functions, that is true with every function you might ever see. And so my x plus 2 tells me it's going to be going left 2. But that does not mean that I'm going to go over and put a point right there, left 2. Because at the same time, I also have to deal with the other shift, which is that plus 5. That plus 5, well, it's hanging on the end. It is not locked in with the x there. Therefore, it is moving it up and down. This is the one that happens like you think it probably should. Plus is actually going to be going up for you. And so my first point is going to be left 2 and up 5. That's my first point. The critical point, when all is said and done, really. Because once I know that point, really, from here, all I'm graphing is just the parent function. Y equals the square root of x. It's just that when I graph the parent function now, instead of it all being relative to 0, 0, it's all going to be relative to my starting point there. So, when I graph the square root function, remember we start at 0, 0, that's the one that I have there, and then we go over 1, up 1 from my starting point, and then we go over 2 and up 4 from my starting point. Now, if you don't remember, why is it over 2 and up 4? Because remember, it's a square root function. And the square root of 4 is 2. So whatever I plug in, that's my x. Whatever I get out, that's my y. So I go over 4 and up 2. Now, what's the next number we can take the square root of? 9. And the square root of 9, of course, is 3. And so from my starting point again, I count over 9 and up 3. And I plot a dot. The next number that I can take the square root after that is 16, but that is off my graphing grid. So I'm not going to worry about plotting that. I'm not totally done though. I know some of you might be thinking, well, this is all we have to do, because on WAMAP you saw some questions kind of like this and it just had you plot the dots. But we are actually making the graph here. So the last step, draw the curve that goes through those points. And so we're going to go ahead and draw the curve in that goes through those. This is what that would look like. This is now completely done. This is our final product that we were looking for. All right, so we're now going to be graphing a linear equation. I know it's linear because there's no other funky functions in here. There's no square root symbol, there's no absolute value, there's no exponents. It's just an x and some numbers multiplied and added to it. All right, so that's how I know it's a line. What form of the linear equation do we call this? Yeah, this is slope-intercept form. Now, the reason why it's slope-intercept is because I can just look at the equation and tell what the slope is and what the y-intercept is. Now, the slope here, that's always going to be whatever is multiplied by the x. In this case, that's the whole negative 2/3. My y-intercept is whatever's added or subtracted onto the end. That's going to be the plus 1. So my y-intercept is actually at 1. Technically, that would actually mean that it's the point 0, 1. But sometimes that just adds a little bit of confusion, so I'm just writing it as being at 1 for the moment. But throughout this course, you're not going to hear me talk hardly at all about y-intercepts. And so what I would actually prefer for you to start thinking about here is that instead of y-intercept, I'm actually going to think of this as a shift up 1. Notice that means the same thing. It still tells me that I'm going to be starting up 1, but because we're going to be shifting all directions like we saw in that first problem, thinking in terms of shifts is just going to help you overall rather than having this special category for the lines having a y-intercept or something. All right, so now when I go to make my graph, I do start by shifting. So I go and put my first point up 1. Then I have to deal with my slope. One little thing that we do have to deal with here is the negative, because I'll see this negative throw people off in the slope every now and then. Does that negative mean that the top is negative, the bottom is negative, or that both are negative? Well, of those three possibilities, actually two of them are okay to use. One of them isn't. The one that doesn't work is making both of them negative. The reason? What's a negative divided by a negative? A positive. If they were both negative, this would be a positive out here, not a negative. So you can make either one of them negative. Personally, I tend to put it in the top just as a matter of habit, and I think of it as a -2 over a +3, but there's nothing special about doing it that way. All right, now what that means then is, again, bringing you back to the idea of slope here, you might be remembering the phrase rise over run. That's a way to help remember that the top number is how far you go up or down. In this case, since it's a -2, as I'm thinking about it, I'm going to go down 2. And then run means how far you go over to the right. So it goes right 3. This is what your slope should be looking like. And you're just going to keep going down 2 over 3, down 2 over 3, plotting the dots. Technically, you only need 2 dots in order to draw your line. And you could get away with 2 dots. But you better be actually using a ruler if you're doing that. Use a straight edge to draw in your line at this point. And then you'll be done. Now the slope-intercept one, this is the one that you started off with way back when you first started graphing at all. And then a year or two ago, all of a sudden we threw in stuff that looked like this and said, graph it. And a lot of you are wondering, well, what's wrong with doing it the old way? Well, this has some definite advantages, and we're going to be taking a look at that. But before we do, go ahead and write it down, take a few moments, think through how you'd approach it. Even start it if you're feeling pretty good about it. All right, now, this is a very different looking equation. What do we call this form? Yeah, this is point-slope form. And the reason why it's called point-slope form is that I can just look at that equation and I can identify a point that is on my graph, and I can identify what the slope is just by looking at the equation. Now, the point part is normally where we end up getting tripped up here. So, let's take a look at how we do this. So, if I were going ahead and graphing this, let's start with what I think is probably going to be the easier part, the +7. Which way would the +7 move my graph? I'll give you a hint. It works the same way that our square root did at the start, right? So which way does the +7 move it? Yeah, that's going to go to the left. Notice it's in with x, which is what tells me that it goes in the x direction, and plus goes left, minus would have gone right. So when I'm going ahead and writing my point down here, that tells me my x coordinate is going to be at -7, because I'm going left 7. But then we have this y -3 over here. Well, at the moment, that -3 might seem like it's in the wrong location, just like it did when we first started our square root equation at the very start of class. Well, similarly, let's think about what would happen if I moved that 3 to the other side. So like if I added 3 and added 3 to both sides, notice over here on the right side of my equation, it would be a +3. Which way does +3 move it? Yeah, the +3 would move it up if it's over on the right-hand side there. Which tells me then, since this must still be doing the exact same thing, this -3 on the left side is actually also going to be moving it up. So when the number is over with y, it's also opposite from what you would think. And so this +3 is going to be going up 3. Now that means my y coordinate is a +3. So when I write out my point, it goes through -7, +3. Now the slope, that part's hopefully easier because the slope is still whatever's multiplied by the x. Now yes, there is a parenthesis sitting in here, but still the 2 is going to multiply by the x. So the 2 is going to be my slope. Once I know that, I can actually make this graph then, because I start at the point that I've identified, the -7, 3. So that means go left 7, go up 3, plot the point there. So basically the only difference between this and the last one when it comes to actually graphing it is that in the last one you're specifically starting on the y-axis. In this case, your first point that you plot is somewhere off in space. It doesn't have to be on the y-axis. But still the same idea. You start with whatever that point is, and then use your slope from there. And our slope is 2. Now remember, slope is a fraction, rise over run. If you're not sure what 2 is as a fraction, write it over 1. Because any number as a fraction is itself over 1. Which means that I'm going to be going up 2 over 1, up 2 over 1, and I just keep doing that all the way to the edges, and then I can grab the straight edge and draw the line in through it. And then if we take a look at our graph, we can see why point slope form, or at least one reason why point slope form is very useful. If I had instead taken this equation and started by trying to solve it for y, which is a very valid approach. If you're not sure what to do with the equation, yes, turn it into something you know. But if you did that here, well, we would have ended up with a problem because it would have been y minus 3 equals, you would have distributed 2x plus 14, and then you would have added that 3 to both sides, and you would have had 2x plus 17, and our graph doesn't fit 17 on it. And so by using point slope, oftentimes it gives us a way to deal with the graph without having to go into some very uncomfortable numbers or create absurdly large graphs or something like that. It often can let us work within the parameters that we have. We just talked about what slope-intercept form looks like. We talked about what point slope form looks like. Formalizing that into our notes would be useful. Most of you remember slope-intercept form, okay, but it's still useful to have that in our notes, especially because we're adding more forms to it. But especially the point slope form, where oftentimes we can have a little bit of trouble. And yes, I did say we're going to be adding more forms to it. Here in a week or two, I'm guessing, we're going to be adding another form to our notes that's going to be fitting in down here of another type of linear equation. All right, and as you have these notes down, one thing to be paying special attention to, because it's the one thing that I'll sometimes still see throw people off, is the whole minus y1 minus x1 thing. By the way, you'll notice subscripts coming back again. Subscripts are often used to represent, different x values. All right, so then notice that the point that this is going through is x1, y1. So that means that whatever that x-coordinate is of some point on my graph, that is the x-coordinate that I put here. Notice the minus in front of it. That's because, remember, we flipped the sign. So like if we're going to a positive x-coordinate, that means we have to do minus that number. But if we were going to the left and getting a negative x, then we'd have to be doing minus a negative, or in other words, plus that number. So just be aware of that. And then we take whatever our y-coordinate is, and we plug that in for the y-coordinate there. And so it's just telling us where we put those. Now I know that point slope form, if anything, is going to be the one that gives us the most trouble. So I want to do one more practice problem using the point slope. But this time I think you can go ahead and do it start to finish. So go ahead and make this graph on your own. All right, and so for this one, the point that we're going through is going to be at 1, negative 5, because it's telling me to go right 1, and it's telling me to go down 5. And so we're going to go right 1, down 5, plot that point, and that's going to be our starting point. And then we use our slope of 1/2, remember rise over run, so the top number is how far we go up, the bottom number is how far we go over. So up 1 over 2, all the way out, or at least out far enough where you can break out your straight edge and draw the nice straight line that goes through them. And then you're done with that one. All right, now we're going the other direction now, and this is where things can get a little bit tricky, right? Because there's some questions that come up along the way. For instance, like if I'm going to write point slope form, which point am I supposed to use? Any of them. The point that you choose can be up to you. Personally, I like to stick with the integers. I like to avoid trying to guess at what a decimal or fraction would be. So, I might grab this point or this point. or this point. In fact, there are a number of different points that I could use along here, and I can actually grab any of them. It doesn't really matter which one. Let's see here. I'm going to go ahead and use this one right here. That's basically an arbitrary choice. I like picking that point mainly because the 5 and the 1 are very different numbers, so as people are looking up here and counting, it'll be a little bit easier to see where the numbers come from when I write an equation. All right, so then, point slope form. It has to be y minus y1, right? That's our general form of the equation on the left-hand side. So what is the y coordinate that I'm going to be using in this particular case? Yep, it's 1. And so for this one, I'm going to be doing y minus 1. Okay, equals. Now it's m times the parentheses. So that's the slope times the parentheses. What's the slope in this particular case?
3.
Yep, it is 3, because you'll notice from any point to the next, I'm going up 3 and over 1. So that's going to be 3, parentheses, x minus x1. And again, x1 is the x-coordinate of the point that I chose there. And so my x-coordinate there is going to be 5. So I'm going to be doing x minus 5. And that's it. That's my whole equation. Now, just as a side note, I'm going to go a little bit sideways here, and I'm going to pick one more point and show us what that would look like. What if I'd chosen that point down there instead, over at 2, -8? What would that change? Well, instead of being y minus something, it's going to be y plus, because we start by doing y minus the y coordinate. But since my y coordinate here is -8, minus a -8 is the same as +8. Now, did my slope change at all? No. The slope is the same throughout the entire line. And then it's going to be x minus the x-coordinate, which is a +2, so that's just going to be x minus 2. Both of those are valid answers, and there are many other ones that you could come up with as well. That's just 2 examples. All right, now we need the slope-intercept form. What's the y-intercept? Well, some of you see it, which is good, but hold that thought. Can you just look at the graph and tell in this case? No. One of the benefits of point slope form is that it saves you from having to kind of do the counting thing, which is probably how some of you at least were getting that y-intercept, which is excellent. That's good. So like you might say, okay, well, if I go over 1 and down 3 here, I could go over 1 and down 3 here, and that would take me to my y-intercept, and you could figure it out that way. But you could also take either one of your original graphs or original equations. I'll grab this one just because I like the color. And you could actually turn that into slope-intercept form. You could use that to get there. So like the first thing I might do is distribute in the 3 and turn that into 3x minus 6. And then I could subtract the 8 from both sides. And so we end up with y equals 3x minus 14. So it turns out our y-intercept is at -14. We can't necessarily just look at the graph to figure that out. We could kind of reason our way through to figure it out, but you can't necessarily just look at it and know. And in those sorts of cases, point slope form can also be very useful for that. So that's one other use for it.